determined by the work function of the metal. So in the presence of an applied electric field, whether it's an AC electric field or a DC electric field, then electrons can tunnel over this work function into the neighboring particle. And this tunneling will significantly impact plasmonic properties. One of my colleagues, Javier Itzpura, had performed density functional theory to account for the effects of electron tunneling between two plasmonic nanoparticles. So here's the density functional theory calculations for separations between about 0.7 nanometers and minus 0.5 nanometers, corresponding to this part of our experimental data. And apart from here the intensity being a little bit stronger, you'll notice generally the trends show very strong agreement, with the bonding dipolar plasmon not exhibiting a strong redshift with the intensity dying off, and then with the charge transfer plasmon also not having a very significant intensity right when they're touching, but once the particles have overlapped a little bit. Okay, so what's the take-home message of the second part of my talk? It's that electron tunneling between two classically sized objects can significantly impact their optical resonance energies and also their electromagnetic field intensities. I think the coolest part about this experiment is that it shows that quantum effects on the nanoscale can significantly impact far-field optical properties. So while you might expect to see a surface plasmon resonance at an energy of about 3 or so electron volts, if the particles get close enough, basically you see no far-field scattering signal by virtue of electron tunneling damping out the surface plasmon resonance. So it's a really neat far-field signature of a purely quantum phenomena. Okay, in the final part of my talk, I wanted to show you what happens when we have 3 nanoparticles. We talked about 1, we talked about 2, so hopefully we're at a point where we can understand what's happening with 3. So let's consider 3 60 nanometer silver nanoparticles.